as I was saying, my name is Matei Istoan. I'm a researcher over at the University of Versailles in France, and I'm a member of the Llvm research laboratory and also of the exascale computing research lab, where Intel is a partner. And today I'll be telling you more about our experience in trying to simulate and execute code using custom precision mathematical libraries. This work is done together with Defour, Pablo Oliveira, and Petit. Okay, so I'll start by telling you more about some of the pitfalls in which we commonly tend to fall when dealing with floating point code. So I need to stress something which I feel that is going to be obvious for many of you, which is that floating point numbers are approximations of real numbers. So yes, the FP, the floating point standard IEEE 754 is a carefully designed, highly engineered system, which has been empirically proved to be a really nice trade-off over years, but you need to be careful about the fact that they are approximations, which means that your inputs can, when you go from the real world into computer arithmetic, your inputs might actually just be approximations of what you're expecting, and your results might be approximations of the real mathematical result. Another thing which is sometimes surprising is that your application might not need all the computation your computations might not need to fully utilize the underlying hardware. So yes, your computer might be able to give you 52 bits of accuracy, but maybe your application doesn't need the 52 bits of accuracy. So in this case, there's an opportunity of optimization that opens up. So this is some of the work that some of the reasons that motivated the work that I'm going to tell you today. And the last point that I need to make, we need to make the difference usually between precision and accuracy. So by accuracy, I'm going to mean how close am I to the true mathematical result. So how close is my computation to the true mathematical result. And by precision, I mean how many significant digits can I compute on a given format? Or if you want to say it this way, what's the maximum accuracy which I can achieve on a given format? Okay, having said this, so let's take a look at the sort of the trade-offs that go between having more performance or more accuracy. And I think the general consensus is that if you want to have more accuracy, then you'll get less performance. And let's try to look at this the other way around. What happens when your accuracy decreases? Okay, so ideally, you'd need to use up less energy because you're doing less work. You'll have less latency because you're handling less data, and you'll increase your throughput. And to illustrate this, we'll take a look at in the Intel MKL vector mathematics library. So MKL stands for math kernel library. And the vector mathematics is the vectorized version of it, but it's not just for vectorized operations. And I'll talk a bit more about this later on. So why choose this? Because as opposed to many other libraries, the MKL gives you a choice in terms of the accuracy of your computation. So they have 3 modes. The first one they call high accuracy, which for the expected performance is the default. And then in terms of accuracy, you get 1 ALP. So I'll tell you more about this, about what this ALP stands for, unit in the last precision. But for now, just consider the fact that the lower it is, the better it is, and 1 ALP is really good. Then you have the low accuracy mode. In terms of performance, then you're giving up a bit of accuracy. You're only getting a maximum accuracy of 4 ALPs, but then you have better performance. And then you have enhanced performance where you get the best performance, but the trade-off is that your error could take up half of your mantissa. So half of half of your computed result might be wrong. So in terms of numbers, then if you look at in the two graphs at the bottom, we had a look on the error function in double or binary 64 and the exponential. So for the error function, you can see that in terms of performance, it takes 9.15 cycles to execute in high accuracy, and then you get an accuracy of 0.75 volts. And this is by all means really good in terms of performance for evaluating this function. And then low accuracy, you get an execution time of six cycles and a bit. And then in terms of accuracy, you double your error. And then when you try to get the maximum performance that this library can result, then you go to enhanced performance, and you can execute it in 5.8 cycles, but then your accuracy is monstrously larger. And it's the same kind of story for the exponential. But you see that there is a sort of a trade-off where you go from, so you have a significant gain where you go from high accuracy to low accuracy, but then the gains in terms of performance when you go from low accuracy to performance aren't as significant as they were in the previous jump, but the error is clearly degraded. Okay, so then let's take a look at what the current state of affairs is in terms of mathematical libraries. So one of the first questions would be, what kind of floating point formats are supported? So it's typically binary 32 and binary 64, which are for floats and doubles. And then you're starting to see some support for 16 bits. For 128 bits is non-standard. So it's usually done with the LibQuad versions. And then you have multi-precision, which are very costly in terms of performance, in terms of the performance hit actually. And then you have limited support. So you're more or less on your own when you want to go to something this extreme. Okay, I need to clarify up some of the concepts which we'll be using before. I mentioned ULP. So it stands for unit in the last place. And it's the difference between the two finite floating point numbers nearest to x. So even if x is one of them, if you think of a number on the axis of real numbers, then that would be the difference between them. As I mentioned before, so ideally your math library should have an accuracy of less than 0.5 ALPS. Which is also sometimes referred to as correct rounding, and this is very good. So it means that all of the bits in your result are correct, and then you have also accuracy which is up to 1 ALP, which is sometimes referred to as faithful rounding, which is more than acceptable. Means that the error might be on your last bit. Okay, so but what if you want to use a different format? So I talked about the fact that binary 16 is getting more and more popular. Then also B float is getting more and more popular. So what happens if you need to do something involving the math library and you need these formats? Or what happens if you need to have the computations which are more accurate and you need something like extended precision, so 80 bits. And then there's the discussion about different accuracy targets. So it's not by chance that I gave you as an example the Intel MKL as a standout example in the first slides. It's because they let you choose at least some sort of targets, and there's published data about how accurate they can be through simulations. But usually you only have one default implementation and then the accuracy is mostly specified in the documentation. And then you have options such as the fast, let's call it a fast implementations. Most languages have this, this concept. In C, this would be the fast math flag. But then you have questions of how accurate is it actually? And we've had a look at it, and this is not always really rigorously specified. And also there's questions of, is it the same accuracy for all functions? And this is usually not true. And then, of course, then the warnings that come with this is, what does it break? Okay, so there are advantages, like it's faster, but then in terms of performance, you need to know how fast is it, and is it actually worth it? So if you're still not satisfied with all of this that I've presented, then what's left? So because after having a look, most libraries that are accessible, then they offer almost the same trade-offs. So this motivated our work in trying to see whether we could look into having custom precisions for the math library. This is a bit of a context. The work that I'm going to describe is part of the Verificarlo open source project. Verificarlo is an open source framework for floating point verification, debugging, and optimization. Has as objectives testing the numerical stability of code, ensuring numerical portability across hardware and software, and then trying to achieve performance optimization, mixed precision explorations. It's available on GitHub, and I'll have a couple of references if you're interested in reading up about it. So the workflow in Verificarlo is based on the Llvm compiler. It's based on instrumenting the code, which happens just before the code generation. Also, Verificarlo analyzes the code after optimizations, so you keep the compiler optimizations. There are two main backends in Verificarlo for the time being. One being based on Monte Carlo arithmetic, and the other one being based on executing variable precision code. So the work that I'm going to describe is based on the variable precision backend, which is called VPRAC. It was initially intended for mixed precision explorations. You can execute code in a format, in a custom format, with any range and precision that fits in the original type. It also handles denormal and special values. And in terms of precision, you get faithful rounding. For the time being, before the work that I'm currently describing, only the basic operations were supported. So you only got addition, subtraction, multiplication, and division. You can use VPRAC in order to perform explorations, code. So you can, there are heuristic algorithms to explore lower precision implementations of an algorithm over time, which would allow you to change precision and depending on your execution. And you have on the bottom an illustration of what I was saying before, that you can, so for example, this is what it would look like when you try to simulate binary 16 inside of a binary 32, so of a float. You see that you only use a part of your exponent, and then you only use a part of your mantissa. Okay, so let me tell you more now about the actual work. We call it VPRAC Llvm, and it allows you to simulate variable precision mathematical libraries. On the top, you see here an overview of the flow. So you can simulate, and as well then explore, as I mentioned in the case of VPRAC. The library computations are done using binary 128, so on 128 bits, using the libquad math. And you can emulate operations that fit on binary 32 and binary 64. Its output accuracy is faithfully rounded, and let's say that this is for the time being precise enough, being as it's more at this stage is a research tool. We wanted to see what we can do before going even more in terms of efforts of trying to get correct rounding. You get the same vprec features, so you can have your inputs rounded to a user default format, you can have your outputs rounded, or both. So the flow inside of the library, we implement this through library preloading using LD preload, which is a mechanism that allows you to load your custom libraries before the system libraries, which effectively overrides them. In this way, we can intercept and replace the mathematical libraries which you normally use with ours. An advantage here would be that your program doesn't need to be modified, and it also doesn't need to be recompiled. So the disadvantages would be that we have a bit less flexibility and in terms of cost as well of executing this. Okay, so there's two modes. First of all, we do a first profile run in which vprec Llvm creates a profile of the calls to the library function, and we document which functions are called. So which tells us what functions are needed in the Llvm when we'll generate a custom one, if we want to generate a custom one at the end. And then we'll get the frequency of the calls, which gives us an idea of which functions should be more or less optimized inside the Llvm that we generate. And then we also get the domain, which will help us compute the formats to use and also give us a sort of an idea of what optimizations can be done. And then you get sort of a basic profile configuration for future calls of to vprec Llvm. And by configuration, I mean an association between the function and the function which is being called and the precision, the format which you're using, which by default is going to be the format that you're executing. So this is what the code file would look like. You don't need to waste your time parsing it. Is just to say that this is still human readable, so you can go through it and see what you get. You get an idea of the type of function which is called. Then you get information on what's the call side path. Then you get the number of calls and the information on the arguments to the function. The next step is then to explore the possible configurations in order to try to find an optimal one. And by the optimal one, I mean a configuration where all formats are set to the minimal possible one, so as to satisfy a given criteria that the user sets. So for example, if you want your output to be identical to the original one, then you can set this. Or if you want to have your output at 95th percentile, for example, that's also acceptable. That's really up to the user to decide. And then we gradually reduce the precision of the vprec Llvm functions. We do this in a heuristic manner in order to go from the most performance impactful to the least impactful. Also, we try to automate as much of this process as possible. This is almost entirely scripted, so you don't need to intervene. And then at the output, you'll get the floating point range and precision. which looks something like this. This is actually for something that I'll talk about later on in the examples. Again, you see the function which was most called, where it was called, how many times it was called, and then you see that it actually only needs 7 bits for the exponent and 2 bits for the mantissa. Okay. So this is all well in terms of the research side and in terms of trying to see the effects of simulating custom precision formats on the effects on the mathematical library and on the code, on your code. But then we wanted to see in terms of performance that we could gain or lose, well, what happens. And so this is where we're using the Intel MKL-VML, so the math kernel library and the vector math library, which is, it's a math library optimized for Intel architectures. It's vectorized, but not only, and in the examples which I'll be discussing further on, we won't be using it in vectorized mode. In terms of data formats, you get support for single precision and double precision. And as I said, you get 3 accuracy modes: high accuracy, low accuracy, and enhanced performance. So I'll talk a bit later on about our exploration using the Intel MKL-VML, and we sort of encoded them in terms of the different modes in different data formats. So for 0, we're using binary 32 in enhanced performance, which would be the least precise, but also giving you the most performance. And it goes up to 5, which would be binary 64 high accuracy, which is the most precise, but also the most costly. I'll give an example. We've collaborated with Davide Mancusi and Émeric Brun of the Center for Atomic Energy here in Paris. And they use, we've tried to apply our exploration on a code which is called Patmos. It's a prototype Monte Carlo Newton transport code, and it's open source as well. And the goal of the project is to perform pin by pin full core depletion calculations for large nuclear power reactors. So basically what it does, it simulates the life of a particle from its creation to its destruction. And what's interesting here is for them to try to track the succession of collisions and movements of a neutron through different materials which are made of different nuclei. And there's for each material, there's a different probability of a particle to interact with the nuclei. And they have 2 main objectives, which is to measure the number of collisions and then to trace the distance traveled by a given in a given volume by a given particle. So I've plotted here the call site frequency for Patmos. This is only for a computational kernel, which is sort of a starting point for them as well, but it's complex enough to be relevant. So you can see that their calls are dominated by 3 call paths on 3 call path sites. Excuse me. Which is a call to the square root, to the error function, and to the exponential, which get called something in the neighborhood of 63 million times. And together they make around 80% of all the calls. So see that next up, the next group of calls is at the order of hundreds of thousands of calls, and then you get another group in the order of tens of thousands, and then something in the order of hundreds. So as I said, VPREC-LibM logs the input data ranges. So we can compute, so then from this we can automatically compute the size of the exponent which you'd need on your format. So this could in fact reduce the data throughput that you require. And you can also, we also plotted the data ranges for for Patmos. And you can see that some of them have really reduced data ranges, which is information when dealing with generating mathematical libraries that can prove to be very, very useful. Okay, so this is the more important, the more interesting plot. Here you can see that we tried to, we see the results of the optimization of the exploration. So on the bottom, on the top, you see the size of the exponent. So we started everywhere with 11 bits because all of the code was is done in double precision. And you can see that they actually don't require all of this range for their data. And on the bottom, you see the significant size. So the degree, ideally, you'd like to see a really large decrease here in order to be able to reduce, for example, let's say to reduce from using doubles to reducing to using floats. Unfortunately, so also I forgot to mention that in this experiment, we're trying to get to be accurate up to 10 to the minus 6 in terms of relative error between our results and their results using GCC. I'll talk more about how we measure accuracy and performance later on. Unfortunately, you can see that on the three main calls, we aren't able to reduce a lot the accuracy, but you can see that elsewhere, as you get to calls which have less impact on the output, there's a large degree which could actually be executed in using floats instead of doubles. So you get some benefits. Okay, as I mentioned before, we did an exploration as well using the MKL in order to validate the previous results. So you can see that, oh yes, we can reduce the accuracy modes from high accuracy to low accuracy in 2 of the 3 main call sites, and then basically the same sort of story which you had in the same confirmed for our VPEC exploration. And you can see, you'll see in the next slide how this translates into actual performance in execution time. So I need to go over a few things when we'll be measuring execution times for Patmos. So as a reference, there are several possible references. So the first one would be to compile their code using GCC and the Llvm, and you can see that it takes 2.5 seconds to execute it. And then there are several other possibilities which we've considered. One of them being GCC, using GCC or ICC, and the VML, where all functions are executed in high accuracy. So if you're not familiar, the MKL allows you to set the precision for a function, but globally on your whole module. So we've considered this a sort of a default setting, because it is the default setting where you choose to use the VML because it's known to be precise, but then you don't actually know the effects of using the VML on the accuracy of your code. So you leave everything on default, which results in an execution of 6.7 seconds. This is also because we're using it in, so for the purposes of this experiment, these are scalar calls. And then you have, we've measured the relative precision between GCC and VML and GCC and Llvm, and we see that you get a relative accuracy of the order of 10 to the minus 7. we keep going around that mark of 10 to the 6 or 10 to the 7 because our partners over at the developing Patmos consider that they're interested basically in having 6 accurate digits. So this is sort of a treacherous number because the difference is 10 to the minus 7, but the fact is that the GCC, that the GCC and the VML, using GCC and the VML is much more precise than using the Llvm. And then we also tried using ICC and the IMF being Intel's math library. And then we get a similar sort of execution time and an error of the order of 10 to the minus 9, but this is even
Matt, you are out
complicated to digest, as the IMF is even more precise than the VML. And then the last question, the last option we had was using the SVML, which is the short math vector library, also a library from the MKL, which gives a result of 0.8 milliseconds. So obviously this would be ideally for us to use instead of the VML. Okay, so
Matt, you're out of time.
I'm just going to conclude if that's all right. Okay, I'll be quick about this. So we measured the execution using GCC and the VML and leaving the accuracy of all the calls to in high accuracy. So you get 6.7 seconds in execution time. Then we put all calls to low accuracy. You see an improvement in the execution time. And then all calls to extended precision. And then, as you saw before, we were only able to reduce the precision in 2 of the 3 main calls, which take up most of the execution time. And we get an execution time of 6.7 seconds, which would be somewhere between high accuracy and low accuracy. But that's not all grim. You saw that the SVML has much better results. So we project to be somewhere around here in terms of execution time, somewhere between 0.8 and 0.6 seconds, which would put the execution time compared to what Patmos developers are currently using at a speed up of around a factor of 2 to 3. So if I'm out of time, I think I can answer more. I can tell more to the people that are interested in the Slack channel or here in the Q&A.
Thank you, Matei. We have posted the Slack channel